Yesterday we reached up to here. Okay, so these were the initial days of the developments of electron of the new transmission electron microscope. The scanning electron microscope is much simpler and easy, but the first development was that of the transmission electron microscope. So scanning electron microscope came later. And as we have in the optical microscopy, the transmission and the reflection modes. So the transmission concept was much popular in those days, and probably because of that, people focus upon the transmission. Uh, if the earlier classes were not attended by students, then they can go to my channel. I give a few lectures on diffraction and a few lectures on the imaging, which are very important when you intend to apply, use electron microscope in your studies. And this course contains the various parts and the constitution of the electron microscope. So I am going through these one by one, that how the electron microscope works and what sort of resources are used, how the electrons are produced, how they are thinned down into a very thin beam, then how they are accelerated inside the microscope, then interact with the sample, then projected onto the viewing screen. Sample preparation, we will have a lecture on that as well, that how people prepare samples sequentially, various steps involved in the electron microscope sample preparation, because one of my teacher of electron microscopy in our first lecture was 1993. He told that in the class that when you have prepared a sample for a transmission electron microscope, so 50% of the job is done. So sample preparation is also a big step in the electron microscopy, and I frequently tell you that it is science, but at the same time it is a skill as well. If you are skilled enough, you are careful in doing things, then your results, your job will be much easier. For example, if I tell you prepare that particular composition of ceramics, you try your best, but you can't prepare the ceramics with optimum properties. For example, the highest density, the accurate particle size for densifying, the accurate temperature process, and frequently you come across various drawbacks in your sample. And some people, they may not be very good in science, but they are so skilled and careful that they prepare excellent sample. So along with the science, it is a skill, technical skill as well. And in itself, it is a technique. So many people can operate machines, but they don't know what they are doing. They are trained to operate the machine, but if they don't understand the science beyond that, all processes, then they can work as a technician, but they are not scientists. Because when you reach this level of study in your career, then you become limited to a single material. When you ask people that what was your topic of study, they say the phase in microstructural evolution of China clay, the phase in microstructural evolution of barium titanate, strontium titanate, calcium titanate. This means their study concentrated onto that single material, and you study that single material to such a depth that you are always, you know more than your supervisor and the outside world regarding that particular material. Because a true project is the one which is novel, which none has done work upon before you. So all the material have been studied, but you select an aspect which has not been explored, and in that particular area, you are the leader in that field. And you are a leader because, for example, if you consider the Journal of Material Science, it publishes its volume every month, and per volume the number of papers will be say 20 or 30, and your paper is published. What does this mean? This means that from the whole world manuscript came to that journal, and those 20s were selected for publication or accepted for publication. This means you are a world leader in that field, right? So you reach that level, and when you come to electron microscopy, then you know the electron microscopy of that specific material. At the same time, we usually tell our students to study the field. To study the field means go to the book, read. For example, I am working on barium titanate, and the teacher tells me go study, review the literature. This means that you will go to the relevant research articles. Listen this carefully. You will go to the research articles. In the articles, in the first sentence, you say that barium titanate crystallizes into a tetragonal symmetry. So your next job is to know what is tetragonality, what is symmetry, what is crystal. If you don't know the crystal, the symmetry, the tetragonality, then you can't move forward. So when you are asked to write a review chapter or a review document on a specific material, then start from there. So that each term, if you study one paper properly, then you don't need to go to dictionaries or other books. In one paper, all the terminology is there. But learn it and then move forward. And when you move forward from there, then you have sound scientific background of that material. But by all this, I mean that you are not supposed to be technicians. You are supposed to be scientists. So that is why it is important to know what happens inside the electron microscope. There are these two popular types of electron emitters. One type are called thermoionic emitters, and the other types are called field emitters. And the relevant microscopes are called field emission microscope and thermoionic emission microscope. But thermoionic emission microscope is conventional. So people don't say that its gun is thermoionic emitter, the electron gun. But if it is field emission, then people say FETEM, FESEM, field emission scanning electron microscope, field emission transmission electron microscope, and by this they mean that the electron gun is of that type. And there is a big difference between these two. The thermoionic emitter gun is of that shape, and the field emission gun is of this shape. What you do, what you expect from the electron gun to happily and easily give you electrons, to give you electrons. And now, if the tip is thin, the tip is narrow, thin, sharp. Sharpness means you have more surface than the bulk. Surface to volume ratio is more when the surface is thin, just like you have in nanomaterials, that the surface is more in comparison to volume. When the surface is more, this means the atoms or the electrons are can be easily removed. If I remove an electron from this wall, then I will have to need a lot of energy to reach the bulk atom and then dissociate that electron from that atom. And then I'll need some work function to take it out to the surface of the wall. And if it is on the surface of the wall, then it will be much easier to take it out. That is not in the sense that we can't pull electron from the bulk. That ease is needed because if you heat that area, then heating and vacuum are opposite processes. Heating and vacuum are opposite processes. You increase the temperature of this room, you will see many fibers around. But if this room is cool, then there will be very little dust around. So when you heat something inside the microscope, although the electron gun has its separate assembly, and in comparison to the microscope column, its vacuum is much less in terms of values. No, very high vacuum is not needed, but still vacuum is there, right? So when the electrons are available on the surface of the material, then you need less energy to take these electrons out. So in thermoionic emission, the surface area emits electrons and the source size is rather large, and they say that it is from 10 to 30 micrometer, the tip size, right? The tip from which the electrons are emitted. And in the field emission gun, the source size is about 10 nanometer, a very high electric field, 10 power 6 volts per centimeter is applied there to take out the electrons by the force of the field. The field pulls out electrons from the tip. So the tip must be very thin so that the electrons appear on the surface, and the field emits the electrons pulls out the electrons from the tip of the electron source. Now, as I told you that if an electron has to be removed, then the energy required to withdraw an electron completely from a metal surface, this energy is a matter of how tightly a particular metal holds its electron, and you call it work function. Then, in thermoionic emitters, it utilizes heat, therm. When you hear the word therm means temperature. So it needs heat to overcome the work function of a material. And tungsten filament is commonly used, and tungsten melting point is about 3400 or like that degrees centigrade. So you need a very high melting point element for that purpose, because you are heating the element, the tip, and it should give away electron, but it should not melt. And that is why very high temperature electron sources are needed. And lanthanum hexaboride is more stable in comparison to that. It is also used. These are various sorts of geometries which people make, and these are all tungsten emitters, wires bent into a loop of various dimensions. And as I told you, its sample is WO and its melting temperature is 3410. So you can heat it to very high temperatures, but heating things to higher temperatures shorten the life of the source, right? Because you will damage that, and with time its life will be shorter. So what people do basically, increasing the filament current will increase the beam current. When you apply the voltage and the current starts in the filament, the number of electrons emitting will increase. But when you reach a certain level, then increasing that filament current will not affect the emission or the number of electrons being emitted. And that is called the saturation point. And usually, when they have knobs in the electron microscope, they have usually shown it on the, when you use a microscope, they have written always that if this is a knob and this is the moving part, so they draw a red line here. This means you shouldn't exceed this, because as you see, the tip is in nanometers or micrometers. It is very narrow, very thin, and when you heat it to high temperatures, frequently, obviously, it will be damaged. And the price, I will show you at the end, they are expensive. Although they are nominal in comparison to the price of the microscope,